Hey, hello, everybody. Hey, this is going to be our second lecture of week number 11, and we're going to expand upon what we talked about with momentum and particularly with collisions. Now, I wanted to talk about the inelastic collisions that we talked about in the last lecture. And I don't think I did the math there, but what we end up having, and in order to determine what those equations are, we're going to take the conservation of momentum, m1v1 initial plus m2v2 initial, et cetera. That's conservation of momentum. Here's the conservation of kinetic energy. So 1/2 mv1 initial squared plus 1/2 m2v2 initial squared equals on the other side. And so with that math, you're going to end up getting the following equation. So what we end up doing is we kind of simplify this. We end up getting a combination of v1i squared minus v1 final squared. Take the difference of two perfect squares. We're going to end up dividing this equation by momentum. Through the magic of math, we're going to end up with this equation down here, which says that the relative velocities of between the first two balls is equal to that negative relative velocities after the collision. Now, we can see that this is independent. This is independent of the math, okay? But we could have lots of different solutions there. So in order to calculate the actual velocities given a certain mass, we need to take this equation and plug it back into this equation and solve for it. And that, in fact, is if you do that, then you can get the equations that I gave you the other day. For example, V1 final, okay? So when you combine these two equations, then you eliminate, or you take this equation and this one, and you end up factoring out this V2 final. And this is where you get that m1 minus m2 over m1 plus m2, the quantity times v1 initial, plus 2 times m2 over m1 plus m2 times the quantity of v2 initial. And then we can get v2 final, which is equal to 2m1 over m1 plus m2 times v1 initial plus m2 minus m1 over m1 plus m2 times v2 initial. And by combining conservation of momentum and this equation right here on relative velocities, which is how we get these two equations for the final velocity after an elastic collision. Now, the reason I'm bringing this up is because sometimes this equation right here is going to be useful. And it is going to be useful because we are going to have a question of the day next week in regards to that. So the next topic that we are going to talk about here is a very classic physics problem that has lots of variations. So no doubt in your physics career, you're going to come across this problem or its variations over and over again. And it's called the ballistic pendulum. Okay, now in a ballistic pendulum, this was the old school way to determine how fast a bullet left the gun. Okay, and it's can be comprised of two parts. So what we're going to end up having here is a gun, okay, and it's going to shoot out a bullet, okay, and if you aim that bullet by a big block, let's say a block of wood, then this bullet will embed into this, and as a result, this block of wood hanging from a couple strings there will then swing up as in a pendulum, okay? And we could measure the height. And by taking these two sets of information, we could end up figuring out, for example, what the muzzle velocity is. So our question is going to be, how fast was the bullet going when it entered the block? How fast was it going at right here? Which is also known as the muzzle velocity, because it's not going to lose. It's not going to lose a lot of velocity between where it leaves the gun and enters the block. Okay, that's the old school way they did it. Now they just use a rangefinder, like a radar gun, and then they can be determined kind of right away. All right, so we're going to say that this bullet is 15 grams, 15 grams. And we're going to say that once that 15-gram bullet hits this, let's say it's a 2-kilogram block, it is going to rise up 30 centimeters. Okay, so there are two parts. To calculating this, okay? One is conservation of momentum. Conservation of momentum or conservation of P. We're going to have M1 V1 initial plus M2 V2 initial is equal to M1 plus M2 V final. Okay, so we can see when the bullet embeds, that is an inelastic collision, and the two masses are together, and if the two masses are together, their final velocity is going to be the same. We are also going to say that the initial velocity of the block is going to be 0. The initial velocity of the block is going to be 0. All right, so that is going to simplify some things. So we know that the initial velocity is 0 there. We also know that 15 grams is 0.015 kilograms V1 initial, and that's going to equal to 2 kilograms plus 15 grams is going to be 2.015 times V final. So we can see here that with this equation, we have two unknowns. And in order to calculate that, we need a second equation. And that second equation is going to come from conservation of mechanical energy. Conservation of mechanical energy, which is going to be kinetic energy plus potential energy. So 1/2 mv1 initial squared plus mgh initial is going to equal to 1/2 mv1 final squared plus mgh final. Now, again, this also is going to reduce down to being something much more simple. If we say h is equal to 0 right here at this level, then that would be 0 and that would go away. So we're going to have 1/2 mv1 initial squared. Well, it's the same mass, right? So it's just going to be our initial velocity squared. Once this swings up at the very highest point, its final velocity is going to be 0. So this goes away. So now we're just going to have mgh. And in our case, RH is 0.3. RH is 0.3. And we can also see that our masses cancel out. And if we do a little math, we can say our initial velocity here is going to be the square root. The 2 comes up, and that's going to be 2gh. And that is going to be the square root of 2 times 9.8 times 0.3 for our 30 centimeters. And the square root of 2 times 9.8 times 0.3 is going to give us 2.42. So our initial velocity here is 2.42 meters per second. All right, so now we're going to take this and it's going to go over here. All right, this is where we just need to make a little bit of a psychological adjustment. The final velocity here, where it is entering the bullet or where it's entering the block, that becomes our initial velocity. That becomes our initial velocity of this. And therefore, this 2.42 is our final velocity. And now it's going to be easy because now we can just say V1 initial is equal to 2.015 times our 2.42 divided by our mass, which is 0.015, and our final velocity there ends up being 326 meters per second. So 326 meters per second. If we were to actually look at significant digits, that would probably be 330 meters per second. Okay, but that would be our muzzle velocity. Okay, so that is a ballistic pendulum. So I said that this could be a variation on this. We could start with the initial velocity. We could start with the initial velocity of the bullet, and then I could ask you how high the pendulum would go. I could tell you how high the pendulum went. I could tell you what the initial velocity is, and you would have to calculate the mass of the block. Okay, that's all a pretty straightforward variation. But what we could also have, for example, is we could have let's say a pistol shooting upwards on a block. Okay, and we could see how high this block went this way. Okay, or if we needed to get to a certain height, how many times would we have to shoot the bullet, okay, in order to get it to that particular height? We could have a block on top of a pendulum, and now we're going to have our bullet this way, and we want to know how far it goes. Like you're shooting tin cans off of a post. How far would that tin can go? And we will see this in our next chapter, I believe. We could have a bullet, for example, hit a block, and this block would be kind of stuck right there, and in which case the block would end up being tumbling forward. Okay, so we could talk about that rotational velocity or rotational acceleration. So again, this ballistic pendulum, very classic in physics problems and multiple variations. All right, so you are going to see a question of the day, I believe next Monday, that is going to be a ballistic pendulum, very similar to this problem. So you can use this as a guide. All right, so our next question is going to be and I'm going to move us over here. Let's do this. Okay. And this is going to be a two-dimensional inelastic collision. So what we have talked about from the other day was that if you had two objects hit each other, you would have M1V1 initial plus M2V2 initial would equal to M1 plus M2V final. Okay, because if they hit and stick, the two masses add together for our final velocity, and since they're stuck together, the final velocity is the same for both objects. Now we're going to do this, except now we're going to do this all in the x direction, And we're also going to have the same exact thing in the y direction. So we could say m1v1y plus m2v2y is going to equal to m1 plus m2v final y. All right, so for our example, in this case, we're going to have two cars. We're going to have two cars crash, okay? And we're going to have our first car over here, and we're going to say that this is 1,000 kilograms, and it is going to the east at, let's say, 20 meters per second, 20 meters per second. And we are going to have a second car. And let's say that this car has a mass of 2,000 kilograms, and it is going northeast at 25 meters per second, 25 meters per second. And at which point they're going to collide. They're going to collide with one another. And when they collide right here, they're going to end up moving together at a certain velocity. So we're going to be looking for our final velocity, and we're also going to be looking at what angle. Okay, at what angle would that be? Now, if we had the same mass, of these two cars, and they were going the same velocity, okay, then the angle at which they would go would be halfway, because we would just bisect that if all those things were equal. But here, they are not going to be the same mass, and they're not going to be the same velocity. So we're going to have to work some things out. All right. Now, this looks perhaps a little more complicated, but it's really not bad. So we're just going to take these two equations. And we're just going to plug those numbers in. So I'm going to get rid of this one, and we're going to fill these in a second here. But I want to point out that this right here is going to be our final velocity, okay? And we're going to have this x, okay? So in the x direction, we're going to have m1 v1 initial plus m2 v2 initial is equal to m1 plus m2 v final. Okay, so we know in the first case, these are all in the x direction. The first case, we're going to have 1,000 times 20 plus 2,000 times 25, okay? But if we go back to here, we will notice that this one right here is going at an angle. So we're going to have a velocity in the x and a velocity in the y. And this velocity in the x is going to be the cosine of 45 degrees. So we're going to add cosine of 45 degrees. 1,000 plus 2,000 is equal to 3,000 v final x. All right. So now essentially what we have here is we have this whole thing, and we only have one unknown. So we can solve for this right now, but that only is going to give us this final velocity in the x direction. And we're going to end up doing that in the y direction, as we'll see. And then we'll get our final answer. So we're going to have 20,000, 50,000 times the cosine of 45 is going to be about 35,500. 35,500, and that's going to equal to 3,000 v final. So we're going to have 55,500 divided by 3,000. V final in the x direction. 55 divided by 3 is going to be about 18 point something. All right, let's 55,500 divided by 3,000, 18.5. Okay, so now we know that our final velocity is 18.5 meters per second. But again, that is only in the x direction. All right, so now we're going to do the same thing. We're going to have m1v1 in the y plus m2v2 in the y is equal to m1 plus m2v final y. So if we notice this one right here, the initial velocity of our first object was not going in the y at all, so that's going to be 0. This one would be going 2,000 times 25 times the sine of 45, okay? So 2,000 times 25 times the sine of 45, which is going to give us 35,500. And that is going to give us 3,000 V final Y. We're going to divide both sides by 3,000. And 35,500 divided by 3,000 is going to give us 11.8. So our V final in the Y is equal to 11.8. And you guys, we are not done. We are not done. But essentially what we have here is we have the x direction and we have the y direction. So we're just going to use Pythagorean theorem. And we're going to say V final is equal to the square root of V final x squared plus V final y squared. And that's going to give us our answer as far as the magnitude. That's going to be 18.5 squared plus 11.8 squared square root. So gives us 21.96. So this is going to be 22 meters per second is our final velocity. But that does not tell us the direction. And in order for us to get the direction, now remember, this was 18.5 and this was 11.8. And if we want this angle, we're going to take the inverse tangent of opposite 11.8 divided by our adjacent 18.5. And we are going to take the inverse tangent of that. So inverse tangent 11.8 divided by 18.5 gives us 0.56. I am probably in the wrong mode. I want to go to degree mode. And that is 32.5 degrees, 32.5 degrees. Okay, 32.5 degrees. Now, if we look, now notice that I had north, south, east, and west, north, south, east, and west. So I could say 22 degrees at 32.5 degrees north of east. But I could also convert that, okay? I could also convert that with respect to the north, which would be 90 minus 32.5, which would give us 57.5, okay? And that would have a bearing. In order to get us to the correct number of significant digits, we would probably want just that to 2 significant digits. So we could just say at 58 degrees. And that would be a bearing of 58 degrees. So remember, when you're on north, south, east, and west, our 0 is at north and it goes positive as we go clockwise. All right. All right, so now we are going to go to our last section of today's lecture, which is going to be two-dimensional motion, but we're going to do that for an elastic collision. All right, so I am going to erase some things here, and we will get set up. So we are going to have those same, equations that we had, okay? But we don't actually have to do that with the M1 minus M2, etc., okay? Because we're going to have two dimensions. We're also going to make this simpler, and I'm going to give you a little insight on the game of billiards. Now, you guys have undoubtedly at least played around in the game of billiards at some friend's house or whatnot. All right, so we are going to take, let's say, an 8-ball, okay, and it is going to be traveling in the x direction, and we're just going to say it's going 20 meters per second. And it is going to hit the 2-ball, okay? And if you guys have paid attention to billiards, you might remember that the 8-ball is black and the 2-ball is blue, okay? Now we're going to take this to be an initial velocity of 0 for the 2-ball. Now, if these two things were to hit straight on, okay, then this one would go at 20 meters per second and this one would stop. But what we're going to do now is they're not going to hit directly on. So what's going to happen is this 2-ball is going to go down at an angle and this 8-ball is going to go up at an angle. And here is a little bit of an insight. When the mass of the balls are the same as it is in an billiard balls are going to have the same mass, the angle between those two as they ricochet off center is going to be 90 degrees. It's going to be 90 degrees. Now, if you have if it hits more off center, okay, then the top one is going to deflect less and the blue one is going to deflect more down there, but it's still going to be 90 degrees. For our purposes, we're going to use a nice, easy angle of 30 degrees. And therefore, we know that this is going to be 60 degrees, okay? But if we're using this as our reference, okay, then that 60 degrees is going below the horizon, and therefore it's going to be negative 60. All right, you guys, now we are set up. Now we are set up to plug this into our equations, which are, okay, conservation of momentum. So we're going to have m1v1x plus m2v2x is going to equal to m1v1 x final plus m2v2x final. And we're going to do the same thing for the y here in a second. But remember, our masses are the same. Our masses are the same. So we can get rid of the masses, okay? We also know that our initial velocity of our second ball is 0, and our velocity of our first ball is only going in the x direction. Therefore, this can be simplified into 20 is going to equal to v1 x final plus v2 x final. Okay, now you guys, we still have an issue with the fact that we have two unknowns and only one equation. So obviously we are going to do the y direction, and we're going to get that. So we're going to say m1 v1 initial y plus m2 v2 initial y is equal to m1 v1 final in the y plus m2 v2 final in the y. So we know that neither one of these are moving in the y direction to begin with. So we're going to have 0. And the m's will have canceled out. So we're going to get v1 final y plus v2 final y. And now, you guys, it appears that we have four unknowns. But we know that, for example, v1 final in the x direction, is equal to v cosine 30. v1 final cosine 30 degrees. Okay? So we can now just say this is v1 final cosine 30 degrees. And for the same reason, we're going to have v2 final cosine of negative 60 degrees. Okay? So now we have v1 final and v1 initial. And on this bottom one, for that same logic, we're going to say v1 final, not cosine 30, but sine 30. And this is going to be v2 final, not cosine of negative 60, but the sine of negative 60. All right. And now we're in a situation to simplify this even more. Okay, so we can say on this top equation that 20 is equal to, you guys, the cosine of 30 is equal to 0.87. So we can say 0.87 v1 final. We can say that the cosine of negative 60 is positive 0.5 v2 final. Okay, so that's going to be one of our equations. Down here, we're going to have 0 is equal to, the sine of 30 is 0.5. 0.5 v1 final plus the sine of negative 60 is negative 0.87 v2 final. And now, if we subtract both sides, we're going to get negative 0.5 v1 final, and that's going to equal to negative 0.87 v2 final. The negatives cancel out. We divide v1 final is going to equal to 1.73 v2 final. Now we're going to take this equation and this equation, and we're going to combine them together, and I will be right back. All right, sorry about that, ladies and gentlemen. Okay, so now we're going to take these two equations. So we are going to do a substitution. So wherever it says v1 final, we're going to put in 1.73 v2 final. So we're going to say 20 is equal to 0.87 times 1.73. 0.87 times 1.83. That becomes now a v2 final plus 0.5 v2 final. And now we can say that 0.87 times 1.83 is 1.5 plus 0.5 is v2 final. This is 2. 20 divided by 2 is equal to 10. And 10 is equal to v2 final. Now we're going to take this and we can substitute it in there. And now we can get v1 final. And that is equal to 17.3. And now we have our two values. And if you take these two values and you plug it back into the original equations, you can check to see that you have correctly done that. Okay, so a cool thing about this in billiards, this is handy to know, is that when two object balls hit each other, they're the same mass. So when they deflect, they're going to have an angle of 90 degrees, which can actually help you out in when you are actually playing pool to figure that out. Also, that you're going to see a question like this for a question of the day next week. All right, until then, we will talk to you guys soon.